Hello everybody, welcome back to another video in our Python series. This is Python Unit 3. In this video, we're going to actually code Newton's method. So if you haven't watched our introductory video on the derivation of the formula, definitely go back and watch that first. As a reminder, this is our second method of estimating roots of functions. We covered the bisect method during our MATLAB unit, and now we'll cover Newton's method. So the point of this video is we're going to take the function f of x equals x cubed minus 2x plus 2. We're going to start at the point x naught equals negative 1.5, and then we're going to apply Newton's method 3 times to estimate a root of f. So as you can tell from the title here, this negative 1.5 is a pretty good place to start. We're going to get pretty close to an actual root of f, and in the next video we'll apply at a worse point. So for now, all I've done is I've imported matplotlib and numpy. And let's start by defining f. So I'm going to use a lambda function. I'll say f equals lambda x. And here we have x cubed minus 2 times x plus 2. So there's f. Now we need to get the derivative, and there are certainly fancy ways of computing derivatives in Python, but for our class, let's just code it by hand. So I'm going to say df for derivative f equals, and again, lambda function, so it's going to be lambda x. So this is going to be 3 times x squared minus 2. So run that. Now let's write a function which actually computes. So remember, what Newton's method does is it kind of returns a point for us that's a better approximation of the root, and then we can iterate using that point. So let's actually write the function that gives us that point. I'm going to call it newt equals lambda z. Let's use z. Now remember, what this does is it takes the point and it subtracts off f of z divided by f. Now I was about to type f prime of z, but notice here that Jupyter's highlighted this in red, tell me this isn't defined, it doesn't make sense. How do we actually have the derivative written? We have it with df of z. So I'm going to run this, and now it's a matter of getting our variables defined for this problem. So our starting point is negative 1.5, so I'll say z equals negative 1.5. I know I want to apply Newton's method 3 times, so I could just type 3 everywhere I need it, but later we'll increase the number of reps and see if we can get better results. So here, let's say reps equals 3. Then what I'm going to do is I'm going to create a numpy array that stores the results of each iteration of Newton's method. So remember, we have 3 iterations plus our starting value, so I want to have a numpy array of length 4. So what I'll do is I'll say arr equals np.zeros. I'll start by initializing it to be all 0, and we want this to be length reps plus 1. Then what we want is the first value should be our starting point, so this negative 1.5, so I'll say arr of 0 is equal to z. So this is good. All we've done here is set up the problem, and we've created a numpy array to store the results of each iteration. So now let's go into a for loop and apply Newton's method 3 times. So I'm going to say for I in range reps, what I want to do. So imagine I start at negative 1.5. I'm going to apply newt, and that's going to give me a new point, so I want to populate my array with that. So what I'm going to do, oops, and I tabbed, that should be 4 spaces. So what I want to do is say arr, not of I, remember we're filling in the next spot, so I plus 1 is equal to newt of arr of I. If this doesn't make sense, the indexing, definitely pause and think about it, but just as a reminder, so we first start arr of 0 is this negative 1.5. We enter the for loop, then arr of 0 plus 1, so it's saying the first position, I want that to be Newton's method applied to our starting point, so arr of 0. So I'm going to run this, and now let's take a look at arr. So we can see here, it starts at negative 1.5, and it ends around negative 1.769. If you were to actually look up what are the roots of our function f, this is very close, but we can also see how close we got by doing something like f of arr. So we can see here, this is saying it's 1.62. Then the ultimate point that we get is negative 6 by 10 to the negative 5. So that's looking very good, close to 0. maybe one thing we can do, so just as a test, so remember here's ARR. If I apply newt to this number, it should give me this negative 1.77 da da da. So let's see, I can try newt of ARR. This is the first position, so 1, or maybe even let's just do it with the point so we can make sure. Negative 1.84210.526. And we can see here, that's the point that got populated in this element of the array. Maybe last thing I want to do in this video is plot our cubic function, and we can talk a little bit about how we get all of these points. In the video after, we'll do a more involved plot. We'll plot the tangent lines with it, but for now, let's just look at our function. So I'm going to say fig, comma, x equals plt.subplots. Let's use 1000 points between -2 and 2, so I'll say x equals np.linspace. Go from -2 to 2, use 1000 points. And then let's say x dot plot. So x, comma, and then our function f of x. Oops, and let's see. Hello everybody, future me here. What had happened was back in my import statement, I had missed this .py plot, so that was what was causing some issues. Otherwise, okay, this is what our function looks like. Now let's change the plot style really quick just so that we can see a few things more easily. So I'm going to say plt.style.use and let's use Seaborn Dark Grid. So now it's a lot easier to see, okay, here's 0. Now let's see, remember we start at the point -1.5, so that's here. We can imagine the tangent line, okay, it looks something like this. We can visualize the tangent line. In the next video, we'll actually plot it. But then, okay, what Newton's method is saying is, okay, now go to -1.84. So that's where the tangent line intersects the x-axis. So we can imagine, okay, tangent line, it intersects around here. Then we imagine, okay, tangent line to our function, we go like this. And the next point, it's saying it's around -1.77. So around maybe here. We can imagine drawing the tangent line again. And that's where we get our last point, -1.76. So again, in the next video, we'll do a lot more with plotting the tangent lines. We'll see an example where we plot at a point that doesn't work out as nicely. Thank you for watching. We'll see you in the next video.